I'm talking about geopolymers, an opportunity for small, environment-friendly productions. This is a knowledge that it is totally new for the majority of the participants of this Congress, but it is something that is very astonishing. It has a wide range of applications. What is a geopolymer? It is the result of the knowledge of geosynthesis, geochemistry, rock-forming minerals, silicates or silico-aluminates, and what we get through all this chemistry and synthesis, we are building geological analogues. We are reconstituting nature. That's strange, but this is what we are doing. In fact, we are dealing today with what we call the geopolymerization of clays, of soils, of lateritic soils. And this is one of the constituents of these materials, which is either clay soil or lateritic soils, which in mineralogy is called kaolinite. It has this structure, and it happens that this mineral, this very common material, is capable of reacting with a very small amount of caustic soda, NaOH, or potassium hydroxide, KOH, in order to provide a three-dimensional polymolecular network of combinations of silico-aluminates that are the analogues of rock-forming minerals. So this is what we are talking about today, is to try to transfer the knowledge of the good possibilities of using the resources that are provided by geology in order to get building material that will require practically zero energy to be transformed into a valuable material. We are only dealing with clays because we have to put a name on these materials that contains 15% of kaolinite. In fact, what we are dealing with are what we call sands or soils, and what is very well known in Africa, from Western, Central and Eastern Africa, lateritic soils. And we are using LTGS, low temperature geopolymeric setting of ceramic. And with this system, we can make bricks. Here, this is a brick made out of lateritic clay, but instead of firing it at 800 or 900 or 1000 degrees C, which requires a lot of wood, which requires a lot of fuel and even gas or oil, we'll do it at 70 degrees centigrade. Well, 70 degrees centigrade is very easy to reach. In fact, we can also start at 25. It is very easy to reach. You just take a black plastic film and you go underneath and you get your 70 degrees very, very rapidly. So here we have some examples of the property when we add 3% of the sodium to a kaolinate and lateritic soil, and we show the the increase of strength, this is in compressive strength in megapascal, with the temperature. This is the untreated material, so you see that to achieve valuable strength, you must fire above 1000 degrees C. We get these strengths of 20 MPa, which is the strength of the concrete blocks, already above 85 and below 250 degrees C. So this is a huge potential. We start at 25, but we have 7 MPa. 7 MPa is sufficient to build a regular house. 8, 9 MPa. At 85 degrees, 14 MPa, you get a 2-story building. And then here, higher. And in fact, if you compare the strength of a regular concrete block, we can get the building material just by working up 70 degrees C. And if you want to get structural material, because in a house, in buildings, you need materials that have flex instead of compression. Structural strength around the frames of the doors, of the windows, they can be achieved by just applying a little heat. So here now, a second parameter, it is the influence of the percentage of the chemistry that we have to add to the system. If we add 0.5 to 1%, we get a soil that is stabilized, that can be used. That's a good behavior to water. If we add a little more, 1%, 2.5, we get a water-stable material that, according to the temperature, reached 4 to 25 MPa in compression. And if you add a little more, it's more expensive, but then you get fired brick. So and you get something that has really high value. Let us see what happens at room temperature. 25 degrees C with 3% only of this chemical. After 3 days of compression, you make your brick, you get 4.1 MPa. After 14 days, 7.7, and after 45 days, 8 MPa. That's a good material. Let's increase the temperature to 60 degrees C, which is practically nothing. After 5 hours, you get 7 MPa, and if you take the brick and let it rest for 15 days, you reach 11 MPa. 11 MPa, it is 110 kilograms per square centimeters. And in fact, if you change the amount of the reagents, 1%, 2%, 3%, 4%, if you do it at 85 or at 450 degrees C, then you can increase it from 6 to 15, 12 to 25, 15 to 30, and so forth. So you have a regular choice. You have a technology that is very easy to implement and that can supply a lot of different types of building materials. Here we compare the strength that we get between blocks made at 85 degrees C and between blocks made at 450 degrees C, and you see that the strength that we get is depending on the amount of the ingredients, which is obvious since we are dealing with a chemical reaction. The more you put, the more of the reactive component, which is the kaolinite, will inter-react in the system.